Welcome to this explainer. Listen, I am absolutely thrilled you're here today because, well, we are going to completely reframe how you think about chemistry. I want you to just forget the boring textbooks and those intimidating lab coats for a second. Today, we're looking at chemistry as the invisible rulebook governing the entire universe. It is literally the master blueprint that shapes everything around us. So let me ask you this. What does a rusting bicycle have in common with your digestive system? I mean, at first glance, absolutely nothing, right? But the actual answer is the constant, invisible magic of chemical reactions happening right before our eyes. And, even inside our own bodies every single second of the day. Okay, so here's our roadmap. We'll start with chemistry in everyday life. Move on to real-world chemistry concepts. Decode everyday reactions. Tackle balancing chemical equations, and then we'll wrap the whole thing up with your blueprint for tomorrow. Let's dive right into Section 1, Chemistry in Everyday Life. You really don't need a white coat or some million-dollar laboratory to witness foundational chemistry. In fact, chemistry is simply the study of matter. It's what things are made of, how they behave, and how they completely transform when they interact with one another. Think of chemistry as the ultimate central bridge. It naturally connects physical sciences, like physics, directly to life sciences, like biology. It's just the fundamental study of transformation. Just look at the sheer volume of chemical processes we interact with daily without even realizing it. We've got the rusting of iron gates out in the yard, the digestion of our breakfast, which, fun fact, your stomach acid is actually strong enough to dissolve metal, which is crazy to think about. Then there's baking a fluffy cake, cleaning grime with soap, plants undergoing photosynthesis, the batteries powering the exact device you're using right now, the ripening of fruit on your kitchen counter, the curdling of milk, taking antacids for heartburn, and the combustion that powers our cars. These are all pure chemistry in action. And these same everyday rules, they scale way up to build modern civilization as we know it. 3 massive global industries rely entirely on these foundations. Agriculture, which literally needs fertilizers to feed billions of people. Energy, which drives fuels and sustainable batteries, and pharmaceuticals, synthesizing the life-saving drugs and vaccines we rely on. Moving on to Section 2, Real-World Chemistry Concepts. This is where we go beyond the textbook. To truly grasp these ideas, we've got to step entirely out of the classroom and just look at our immediate surroundings. Think about it like this. If you're assembling a bicycle in a workshop, you take one frame, you add 2 wheels, and boom, you get one bicycle. In chemistry, the ingredients you start with, the frame and the wheels, are perfectly mapped to the scientific term reactants. And that final bicycle, that's your product. A chemical equation is literally just the written recipe for this exact assembly process. Now, let's consider dynamic equilibrium. Picture a crowded metro station during rush hour. If the exact same number of people enter the station as the number of people leaving on the trains, the station remains constantly busy, right? But the total number of people inside stays exactly the same. It is the exact same concept with an unopened fizzy soda bottle. Inside that bottle, carbon dioxide gas is dissolving into the liquid at the exact same rate it's escaping from it. It's constant activity, but the total amount stays perfectly balanced. 180. Whether you're baking a loaf of bread in an oven set precisely to 180 degrees Celsius, or a doctor is prescribing exactly 5 milliliters of a specific medicine, precise measurements completely dictate the outcome. In chemistry, even the absolute slightest change in temperature or concentration can completely alter a reaction. All right, Section 3, Decoding Everyday Reactions. Let's look at the formulas all around us. I just love the beautiful symmetry here. On the left, we have cellular respiration. This is how our bodies get energy by breaking down glucose with oxygen and releasing carbon dioxide. And on the right, we've got photosynthesis. Plants take in that carbon dioxide and sunlight to create glucose, and they release fresh oxygen. The way our bodies get energy is the exact chemical opposite of how plants create their food. It's just this incredibly elegant, perfectly balanced loop. Then we have the Haber process. Nitrogen from the air plus hydrogen gas placed under extreme high pressure creates ammonia. Now, why does this matter to us? Because manipulating these basic elements literally sustains human life on Earth by allowing us to grow enough food for billions of people. In fact, check this out. Nearly half the nitrogen in your body right now comes from this exact factory process. No way, right? But it's true. Okay, Section 4, Balancing Chemical Equations. This is the math of chemistry. I'm going to deliberately slow down our pace just a bit here because we're zooming way into the micro level to decode the mathematical language of these reactions. The crucial point you have to remember is the law of conservation of mass. Matter cannot be created and it cannot be destroyed. Atoms can't magically appear out of thin air, and they definitely can't magically disappear either. This means the number of atoms for every single element must be identical on both sides of an equation. So really, balancing equations isn't some tedious math chore. It's just a highly logical puzzle. Think of it like packing sandwiches for a road trip. If one sandwich requires exactly 2 slices of bread and 1 slice of cheese, you can't just take 5 slices of bread and 5 slices of cheese and expect to magically get 5 sandwiches. It just doesn't work that way. And honestly, nobody wants a sandwich with half a piece of bread. You absolutely must balance your inputs to get your desired outputs. 10 bread slices plus 5 cheese slices gives you 5 perfectly balanced sandwiches. Let's apply that exact same logic to water synthesis. Step 1, we start with our unbalanced equation. H2 plus O2 gives us H2O. Notice we have 2 oxygen atoms on the left, but only 1 on the right. So step 2, we balance the oxygen by adding a 2 in front of the H2O. But wait, look what happens here. Now we have 4 hydrogen atoms on the right. How do we fix this? Actually, it's no problem at all. Step 3, we balance the hydrogen by going back and adding a 2 in front of the H2O on the left side. Our final, beautifully balanced recipe is 2H2 plus O2 yields 2H2O. Now we can act as kind of like chemical accountants. For the combustion of propane, we balance the carbons and hydrogens first. We have 3 carbons on the left, so we need 3 CO2s on the right. We have 8 hydrogens on the left, so we need 4 H2Os on the right. Now let's count the total oxygen on the right side. 6 from the CO2 plus 4 from the water equals 10. This dictates that we need exactly 5 O2 molecules on the left to perfectly balance our ledger. Now here's a slightly trickier puzzle: sodium reacting with water. By the way, this is a highly explosive, violent reaction in the real world, which is exactly why getting the math right is so absolutely crucial. Look at the unbalanced equation. We have an odd number of hydrogen atoms on the right side, 1 in the NaOH and 2 in the H2, making 3 total. To solve this, we force an even number by simply placing a 2 in front of the NaOH. Now we have 4 hydrogens on the right. We easily solve the rest of the puzzle by balancing the left side, adding a 2 to the water and a 2 to the sodium. And just like that, puzzle solved. All right, let's look at Section 5, your blueprint for tomorrow, unlocking your potential. Let's speed things back up. Mastering these foundational rules isn't just about passing a chemistry class. It unlocks immense future potential. If you're aspiring to tackle highly competitive exams like IIT-JE, NEET, or BITSAT, these core concepts are strictly non-negotiable. And listen, these exams don't just test rote memorization. They ruthlessly test your ability to take the basic principles we just covered and apply them to really complex, multi-layered problems. This isn't just schoolwork we're talking about. These are the actual tools that future engineers, doctors, and researchers use every day to design chemical plants, create new alloys, and understand human pharmacology. So we come to our final takeaway. Every time you see a rusting gate, a baking cake, or even just your smartphone powering up, you now know the microscopic molecular rules making it all happen. The universe is speaking a hidden mathematical language all around you. The only question left is, what invisible reaction will you master next? Thank you so much for joining me on this explainer. Keep observing your world, and I will catch you next time.